Okay, let us continue with titration involving weak acid or weak base as sample or analyte with strong titrant. Okay, strong titrant is either strong acid or strong base. Now the approach will be different with strong acid and strong base titration because the dissociation of weak acid or weak base is partial in water. So that's why you see arrow is pointing at both direction here. Okay. So if the sample or the analyte of interest is a weak acid, then we have to use the acid dissociation constant Ka. If it's base, then we use Kb. So to calculate pH for weak acid or weak base, you should know by now because we have covered it in the previous learning unit. Now, similarly to strong acid, strong base titration, we also have to consider the pH before titration, when it reaches equivalence point, and when it over titrate. Okay. Okay, so the calculation involved is Henderson-Hasselbalch equation. Okay, so if sample is acid, then we use pH equivalent to pKa plus log of base over acid concentration. And if the sample start with base, we use POH and PKB, and we minus from 14 to find the pH. And the denominator would be the base concentration. So means that for base, it's the opposite of acid. Okay. So what happened at equivalence point? Okay. So at equivalence point, all of the sample will be converted to its conjugate form. So if you start with weak acid sample, means at equivalence point, all of the weak acid sample has been converted to conjugate base. Okay. And then calculation of pH at this point would be using Kb because no more acid is present, so we have to use Kb expression. Okay. And if the sample is base, then we have to use the opposite. Okay, we use Ka instead at equivalence point. For over titration, it is similar to strong acid, strong base. Okay, so only this part is similar in terms of calculation. Okay, to understand this better, this is the example of titration involving weak acid with strong titrant. So in this case, the weak acid is benzoic acid, 0.1 molar, and the volume is 100 ml. And it's titrated against 0.1 molar sodium hydroxide, strong base. And you are also asked to construct a titration curve. Okay, only for weak acid and weak base cases, you need the Ka or Kb value. Okay, so to find pKa, you negative log Ka. So Ka for benzoic acid is given here. Okay, 6.31 times 10 power negative 5. So we negative log this value, we get pKa. So first step is to find the equivalence volume. Okay, at equivalence point. So you have to use M1, V1, M2, V2 formula also. So the concentration are the same. So means V2 or the volume of sodium hydroxide needed will be 100 ml also. So that is the first step. Second step is to find pH before titration. Now, for strong acid or strong base, you just negative log the concentration of the sample to find the pH, but not the case for weak acid or weak base. We have to use Ka. Because why? Because they are partially dissociate. Okay. So the sample is weak acid, weak benzoic acid is now. So we use benzoic acid Ka to find the pH before titration. Okay, using this expression here. Okay. So Ka is given just now. Okay, so the expression would be x squared over 0.1. Okay, we get this from the expression in the previous formula just now. Okay, this one. Okay, this. Okay, when it dissociate, you get H3O plus and A minus. Okay, and this is the original concentration. So you put it in the expression here. Okay, why? Because we need to find H3O plus, the dissociate. Okay, so H3O plus here would be 0.0025. Then we negative log this concentration to find pH. That's how we calculate pH for weak acid or weak base sample before titration. Okay, unlike strong acid, strong base, you just negative log the concentration. You negative log 0.1, then you get the pH or pOH. Okay, then the third step would be after you have start titrating. Now, when you already titrate, what happened? Similar like acid, strong acid, strong base titration. What is reduced and what is produced? Okay. So you have covered this in the previous learning unit. Okay. It's like you are adding strong acid or strong base to a buffer solution. So you see the approach is more or less the same. Okay. So because base was added in the as titrant, so the amount of acid would reduce. So that's why you see a minus sign here. Okay, so initially in the Erlenmeyer flask, you have 100 ml of 0.1 molar benzoic acid and 10 ml of titrant, 0.1 molar was added. Okay, and this is the new volume after mixing. Okay, after the titrant had been flowed into the Erlenmeyer flask. So now this is the new concentration of the acid because some of it has counter addition of the base. Now how to find the mole of when the acid was added, when the base titrant was added, conjugate base was formed. And that's why we calculate here moles of sodium hydroxide added. Okay, so moles of sodium hydroxide added from the molarity and volume, okay, which is 10 ml added just now. Total volume becomes 110, okay, and this is the concentration of the conjugate base form. Okay, once you get the new concentration of the acid as well as the conjugate base, then you substitute them into the Henderson-Hasselbalch formula to find pH. Now, Ka was Ka was given, so you can calculate pKa. So you divide first, okay, the concentration of base over acid, then you log, then you plus 4.2. Then you get pH. That is the addition of 10 ml of titrant. You do it the same when you add the subsequent 10 ml of titrant. And it has been done for you here. Okay, 20 ml, 30 ml, 40 ml, and so on. And we know just now we have calculated in the first step that the equivalence volume is 100 ml. So how to find pH at equivalence volume? Now the approach is very different from strong acid, strong base. For strong acid, strong base, pH at equivalence will always be neutral, which is pH 7. But for weak acid or weak base sample, we have to use Kb because now all of the acid has been converted to conjugate base. Okay. So we have to use the Kb expression now. Okay. Because no longer benzoic acid present. So we have to use Kb. Okay. How to find Kb? We use the Kw, Ka, Kb expression. So to find Kb, Kw divide with Ka. So we have Kb, sorry. Kw divide with Ka to get Kb. So this is the Kb value. Okay, so we substitute this in the expression to find OH. Okay,